Again, welcome to the second session today. Today is Wednesday, March 17th. Today we're going to be talking about the lab actually. And this is LAB02, which is really introduction to capacitors. So let me get into the lab instructions first of all. Let me pull that page and share with you the screen. Share this page. Okay, as you guys see in here, there is the instructions for the lab and everything and when the stuff is due. So it's in about 10 days from today, it's due. I want you to have your attention for this part in here, which is the rubric, okay? It's very important that you guys follow the rubric. The rubric is part of all the labs that I do, and your labs are graded, or actually everything that I do is based on a rubric, so please pay attention to that. And make sure you follow it. Make it some sort of a guidelines, basically, for how to answer everything in there. You see exactly how much points you're going to get for every single item. Usually the questions are worth 2 points, and they're graded as such. And then if there is a single value that you're supposed to report, it's worth 1 point, like this one's in here. And then tables are worth more points. In here, you have a table that has basically 80 cells. So if all of them are entered correctly, you should get 80 points for it. And if there is a partial credit or so on and so forth. There is a graph in here, so you need to include that. That too is graded, and you know exactly how much graphs are worth in here. And also there is another graph. So there's a lot of things in here, and graph and questions and graphs and data. So I want you to really pay attention to these things in here until you finish everything. You're going to earn 171 points, including the conclusion, of course. Okay. So this is basically something that I want you to pay attention to while you're doing this thing. So I'm going to stop sharing that screen, and I'm going to find the other page that I'm supposed to be with you on, and that is the lab instructions. So let me first of all go to the beginning of that, and now share this instructions in here. Is everybody looking at lab 2? Physics 4B.
Yeah, we see it.
Okay, very good. So again, some of these fields are required, some others are not, but please make sure you include everything if you want to have full credit for this lab and do all of the activities related to it. Your name is important. The name of the people who work with you is important. So if you happen to work with somebody else, which is actually very good, you're encouraged to do that. Please do so. Let me know though in the lab report, okay, that you worked with so-and-so. Please observe all the safety rules and requirements by basically the health experts when you do that. So it's very important. Usually I leave the objective toward the end if I'm doing this, okay? Because I really need to understand what I'm doing for every single thing in here. The objective has to be comprehensive. It has to describe everything that you're supposed to be doing. Not the minor things that lead to the ideas, but the big ideas, yes, okay? It has to be complete sentences, and it's usually one paragraph, okay? I know the requirement in here is what, like 2 sentences or more? Don't write 2 sentences because that's too short. Don't start counting, okay, how many sentences in here you have. Try to be descriptive and accurate in your objective. You should not use I pronoun. You should not use the student, the noun, okay? You should put it in the general sense, like we, for example, are going to explore. So that is proper way of addressing the lab. Or in this case, the lab is about the capacitance. Capacitance will be, okay? So in that tense, okay? So the tense is very critical when you're writing your lab report or communicating in science in general, okay? So that is basically the proper way on how to structure this one. So in the beginning, it's not going to be that big of a deal, but down the road, I'm going to be picky about even those minutia. Everywhere you have a spell checker, so please take advantage of it. Don't have typos in it. Do not write, for example, capacitance. Okay, that is sometimes it complains about that. Okay, when you have a word that is scientific, and then it tells you that it is not spelled correctly. Okay, so again, you're supposed to spell everything correctly. You see here, that's my point, that there is actually a rich text environment where you should take advantage of it. Spell things correctly, okay? So and then of course the grammar too. I'm not teaching you English, so I'm not going to be picky about that, but your idea need to be clear. What you're saying need to be accurate. That I care about. You need to be very specific in your description. So if I find it a vague, no connection, or somehow throw in some stuff related to the lab without really going specifically to what we're exploring in here in this lab, that is not correct, okay? You're going to lose points that way. So you have to be specific in your description, accurate, and describing of what you're doing in the lab. Because of this requirement for the objective, I will defer it toward the end, okay? The objective and the conclusion need to be connected somehow. You cannot come to the conclusion and start talking about a different topic than what the objective was supposed to be. So in the conclusion, you need to address the points that you raised in the objective and how you basically were able to verify them, or how you are able to check them, and whether or not they worked or there was issues or something like that. So don't forget that. That has some implications down the road. Now, the conclusion also has additional stuff. The conclusion usually has numbers in it, data in it, to support whether or not what you arrived to is correct or not. Don't list every single piece of data, the main points, okay? And in that sense, also, with what confidence do you think numbers make sense? So you need the conclusion to include also some sort of an error analysis. Again, you're not going to list for C1, this is how much, for the other capacitors. No, the overall, okay? If there is, for example, an error of 2% in here and 3% in here and 1.5% in here and a 7% in error. So that 7% stands out. So all of the error that you say that they were within this much, between 1 and 2%, they're to some extent acceptable because of this. But this error, then you can talk about that one. Otherwise, you're going to talk in general about the errors, how they stand, okay? So that is how usually conclusions are. Specific errors and specific results are addressed in the questions themselves. Usually before and after an activity, there is a bunch of questions before and after. That is when you talk about those specific errors and what they mean and all of that. But the conclusion also, there is room for it, for that too, because now you're trying to summarize everything and communicate it and how it's connected to the objective. Does it make sense to you guys? The plan overall. Good? Okay, so.
Yep.
Okay, very good. So now question 1. Remember, this is just fresh from the oven. We're doing capacitors and charges and voltages and everything else. So it says in here how much charge is stored in 100 microfarad capacitor with 50 with 15 volt. This should be straightforward, okay? And now if you double the voltage, how does the charge go? So a lot of these questions are supposed to basically look at the basic formulas and understand them and answer this question. Yes or no question in a question is not acceptable. So don't come in here and say, if the question says, is the temperature, for example, is increasing, or is something is less, or is this, for example, for this specific question, when I double the voltage, does the charge double? And you answer yes, or yes, it does. That is not good. You really need to be thorough, okay? At least repeat the question with the answer embedded into it. When we double the voltage, it looks like the charge has doubled, okay? At least like that one, or not looks like, the charge has doubled. So you have to be affirmative in your statements too. You cannot be wishy, you cannot be iffy in this situation, okay? You cannot use the word it seems. That was a mistake from my part. So when we double the voltage, the charge doubled, okay? So don't say yes or no. Those short answers are not acceptable either, okay? So it tells you, for example, to find how much charge in here when you put that one. So you're going to do 100 times 15, which is supposed to be 1,500 microcoulombs. So don't put 1,500 microcoulombs. You're going to say for a capacitance of 100 microfarads and a voltage across it of 15 volts, the charge is, and then you put your charge in there, or use the formula and then put at the end the charge in there, okay? You lose points for units in the questions. You lose points if the question is not properly answered. You lose points if the question basically is not structured correctly. So pay attention to all of these details. In other words, show understanding and know that you're doing these activities, okay? So don't be lazy in doing this, because it's very important that you have to really take care of this report as much as possible. The labs are worth 25 points of your grade, so they're extreme importance. This question is easy, and you could have easily lost points in it unnecessarily. Okay, so don't waste time on it, and don't waste basically points on this thing. Go thorough with it. Okay. Now, another question about the entire lab report form that you have before you, it's fillable. If you run out of space, or you don't like it, or it doesn't work for you, it is your job to still submit the lab report. Pick up a Word file or a text file and refer to question 1 from lab 2 and answer it. And instead of submitting this form, you're going to submit that lab report. Is this clear? Yes? It is very good, thank you. It is very important that you do not rely on this lab report form. It's just basically a guide to help you do your lab report. It is not a requirement to have this lab report form submitted. So if it doesn't work for you, if you cannot save it, if you have issues with it, it's still your responsibility to answer all of the questions and do all of the activities in the lab. Okay? You may or may not SAD, whichever you want. It's for your convenience, actually, and for clarity, it's actually the lab report form is preferred. However, if you have difficulty with it of one form or the other, or the space is not good enough for you, because you have more in mind to say than what is allotted, then it's your responsibility to append, either attach, some supplement, or completely brand new one. Make sense to you, Saad? Okay, very good. So, question 1 hopefully is easy enough. And then we have, this is the formula that we arrived to, I think, a long time ago on Monday. C for a parallel plate capacitor is epsilon naught A over D, where epsilon naught, now we're going to be specific because we're doing lab. So we are not going to write that thing that I wrote 4 pi times 9 times 10 to the power 9 inverted. So we're going to go with an epsilon naught, which is this value, okay? What is the capacitance of parallel plates? So now I gave you the area of 100 centimeters squared and separation D, which is 0.1 millimeter. And you want to find the capacitance. So you have epsilon naught, you have A, you have D. Don't forget that A is in centimeters and D is in millimeter. So you need to convert to SI if you expected to find it in farads. So there is a conversion here. Centimeter is 10 to the negative 2 meters. So when you square it, it's 10 to the negative 4. And a millimeter is 10 to the negative 3 meters. So there will be a 10 to the negative 4 and a 10 to the negative 3. In other words, 10 to the negative 1 times 100 divided by 0.1. And then that is multiplied by epsilon naught. You should be able to find what C is, okay? If you double the separation, how does the capacitance change? If D doubles, you clearly see that in this case, the capacitance will drop, okay, by a factor of 2. So that is basically the stuff that is going on with this lab in here. In the presence of a dielectric, I used the symbol epsilon R in the lecture, okay? I cannot write in here, notes, comments. I hate this thing when it happens. Comment. Okay, can I do it with this thing? And it has to be a mouse, actually. I cannot use the pen for this, sorry. So I used epsilon R in lecture. In here, we use the letter kappa. Okay, this letter in here to represent the relative, basically, capacitors. So this is basically compared to epsilon naught. So the vacuum is not 1, but it's 1 times that number, 8.85, 410 to the negative 12. So that is just multiplied by that 1. So the air, the air is slightly different than 1. For Teflon, it's 2.1, and then you start going all the way. This is if you really want to build one in your place, in your home, because sometimes you need to. Like, for example, in the lab, when we used to do it in person, we used to make these capacitors, and we use paper. And paper, the dielectric for the paper is relative dielectric, relative permeability, in this case, 3.7. So in this case, if I want to find the capacitance that I'm going to build with aluminum foil and paper between them, and I need something to separate the two conductors, otherwise the charge will go basically canceled right away. So practically the dielectric is not just needed for that, but also for insulation. So I multiply epsilon naught times the area that I make divided by the distance between the two plates. Usually that's the thickness of how many pieces of paper I can slide in between, times the kappa for the paper, which is in this case 3.7. Okay, that's basically how I go about it. If I don't know the value, and it's roughly made out of this material, so it's going to be a 3, 4, 5, 6, whatever I can, and unless it's a different material, then it's in there. Okay, so we're not doing that now, but this is basically how that is. Okay, now we will use this activity now, and this activity looks like this when you go to it. So we're going to be pulling a voltmeter. We're going to, I don't know why we need the electric field in here. We need probably the electric field just to visualize it. This is the battery. The battery is you're going to turn on and off between 1.5 to negative 1.5. In other words, is it 1.5, or you flip the polarity of it and it's going to be 1.5 in the opposite direction. So that is how you build charge. You're going to have the stored energy in 10 to the negative 13. So this is a very, very tiny energy. So this is of the order of a femto actually joule, okay? And the same thing in this case is the charge in coulombs, basically. So this is actually of the order of what? 8.5 times 10 to the negative 12 microcoulombs or something like that. So that's actually less than that. 0.085 picocoulomb. So this is going to be a very tiny charge. Unfortunately, these are the limitations from this one, because it's trying to mimic what you actually do in the real life, okay, as you build them yourself. But as you have this capacitance is in from other devices. Let me grab my Arduino board in there quickly. Let me see in here how much capacitance this one is. This is a 47 microcoulomb. Microfarads. Okay, what are they? Here. So they are very tiny. They are actually very large compared to this one. Okay, so this is an Arduino. It's an old Uno Arduino, not the version 3 that is out there now. Anybody played with these things? Arduino boards? No? Okay. It's a lot of fun, okay? I wish we are back on campus so that we can do a lot of activities, at least with the physics club or... Okay, very good. Very good. At least somebody has had fun with them. Anyway, so we're going to go there, okay? And we're going to start doing this, okay? So first thing in here is that calculate the capacitance. So this is what they want you to do. They want you to set the minimum area to 400 millimeters squared, and they want you to make the separation of 5 millimeters between the two plates. And you're supposed to calculate now C naught, how much it's supposed to be, okay? The capacitance at this point. So let me first of all close this thing in there. And the commenting tool, that was what I closed. And let me find it, it's in here. So let me stop sharing that screen and share with you what you're gonna see. Share, FET simulation. Okay, so I don't think that we need the electric field. I don't think we need the capacitance. So now here is how you change the area. Is this over or not? Still 92%. So we're supposed to have it at 400. It's 400. Now that this distance between them, it's 10 millimeters. So I'm going to drag it down to about 5 millimeters. So this is what you're supposed to do. Okay. So at this point, the voltage is 0. But now I have the area. I have the separation. Can I find D now? I mean C. I have D. I have A. But don't forget, it's 400 millimeters squared. So it's 10 to the negative 3 squared. So it's going to be 10 to the negative 6 at the end. And then the separation is 5 millimeters, which is another 10 to the negative 3 in it. So when you're calculating, you have to be careful. And multiply that by epsilon naught. So it's going to be a very tiny number. Make sense? Okay. So a lot of these activities of this type, okay? So let me go back and share with you the other screen now. All the lab instructions. So now this is the calculation. This is what you're supposed to do. Now you're going to just write the value of D, which is 5 millimeter, or 5 times 10 to the negative 3 meters. And the area is square meters, which is what? I don't forget. 400 times 10 to the negative 6 square meters. And the value of the capacitance that you calculated in here. Please don't just list the value in here, okay? At least refer to this number and this number, and refer to this formula and calculate it. You need to show understanding. You need to show really that you're on top of these things, that you are killing it, okay? You know exactly what's going on. You have nothing is basically escaping you. That's what I want to see through these questions, okay? And now, increase the voltage from the battery and record the values across the capacitor. So this is what we're going to do in here. We're going to go 10 steps, basically, for the voltage. And as we increase it from 0 to whatever, the 10th value. Remember, we're going to go in increments of 0.1. The charge now, we're going to note it in here, okay? The energy, leave it for later on for calculations. You're going to calculate it yourself. Remember, because we have Q and we have C. We have V and C, so technically we should be able to find the energy now. It's 1/2 of CV squared, or however you want to do. Or actually, we're going to get it from the table. I'm sorry. We're going to get this one from the table. We're going to get this one from the table. We're going to get the electric field. We're going to calculate V squared. We're going to calculate Q squared. And we're going to calculate E squared, okay? The energy and the energy density in there. We're going to do all of them. So let me go back in here. Increase the voltage across the voltage, charge Q, and energy stored U. Okay. Okay, so let's go back. Let's stop in here, sharing the screen, and let's share the FET simulation. So we're going to go, we need the capacitance, because it asks us to find that too. Right now, this is what it says. I know you calculated yours, but you need to compare it to these numbers at the end, okay? The plate charge, there's zero charge right now sitting on the plates, on this plate. The stored energy, there is 0 joules right now. And we need a voltmeter. And the voltmeter, you need to grab the negative and put it in here. Right now, it's reading 0 volts, because there is no voltage right now, okay? And this is attached to this plate. So there is 0 voltage right now between the two plates. So if I increase the value in here to, what is the voltage right now? 0.149 volts, okay? So we have the voltage. Do we need the electric field lines? This is how the electric field points down, that's all. But it points from the positive to the negative. And I have the capacitance, should not change the capacitance. I have the plate charge, 1.05 times 10 to the negative 13 Coulomb. I have the energy stored, which is 0.08 times 10 to the negative 13 joules. And I have the voltage in here. If I look at my table, what is my table? So I have V I have C, I have the energy stored, and I need the electric field. The electric field is just basically, do we have, oh man, it does not give me a way of finding the electric field directly. But it's simply equal to E is voltage, which is 0.49 divided by that distance of 5 millimeter. Okay. So that's how much electric field you have right now. But then the table asks that you square the voltage, which is 0.149 squared, and then you square the charge, whatever that value is, and you calculate the square of the electric field in volt per meter squared, and then you calculate the energy, in this case, which is U, divided by the area times divided by the volume, basically. This is the energy density. Let me go back and share with you what I'm talking about in here. Share this table. So remember, the voltmeter will give you the voltage. The charge is there when you display it. The stored energy is also there when you display it. The electric field is just that voltage divided by that 5 millimeter, the separation between them. Now you square this value. You plug it in here. You square this charge and you plug it in there. You square this electric field and you plug it in there. You take this value of U, the energy, and you divide it by the area, which is 400 millimeter from here, from the top, this area, times the distance, which is the volume. Since this doesn't change for this particular case, you leave it as is. So you're going to just take, once you find the volume, all you have to do is just divide these values by it. The problem with this one is repeat it 10 times. Makes sense for you guys. You go from 0 volts all the way to 1.5 volt. Yes?
So we don't do negative voltages at all?
Oh, you're not going to do the negative voltage in here, because if you're going to do the negative 4 volts, what you're doing is just getting the negative charge. Okay? Charge will be flipped, that's all, in the opposite direction. Stick with the positive, it's fine. Okay? Obviously, when you square the quantities, they will be symmetrical. The electric field will flip sign because it's going to point from bottom to top. The energy should stay the same for the same voltage, because the energy has nothing. It's always the square of the charge or the square of the potential, and those will change. Okay, that's all. Okay. Make sense? Okay.
Makes sense.
So, very good. So let's continue with that. Oh, where's are you guys? Oh no, you're not. I'm sorry. Share. So we're supposed to have finished all of these questions. And now we're supposed to graph. We need to make a graph of U, the total energy, as a function of V squared. So this is your dependent variable, and this is your independent variable. So this is your y-axis. This is your y-axis. This is your x-axis. So when you look at this graph, this is going to be the voltage squared, not the voltage. This is the voltage squared, and this is going to be the energy U. Remember, 1/2 of C times V squared is equal to the energy. So the slope should be exactly 1/2 of that C that you calculated. You calculated above. Can I change the fifth one page? Remember, you calculated C at some point from question 3? This is your calculated value. And you actually, the table have C in it too. No, the table does not have C in it, but no. This is actually the measured, this is the calculated C naught. So now when you measure this value, it's going to be new C now, not necessarily that of C naught. So use this equation to determine C naught using the slope. So now you have a different value for the capacitance that's coming from this slope, okay? Coming from this line. You're going to find the error by comparing this measured C naught versus what you have measured here in question 3. Make sense? This is going to be a percentage error. Yes?
Yeah, that sounds good.
Okay, very good. So there is one that is coming from the chart and one that is coming from the calculation. You need to compare the two and see how off are you from the theoretical and the experimental. Same thing. You're going to take Q and draw it as a function of Q squared now. Remember the expression. So you have, first of all, you have this will become your independent. I'm sorry. This is going to be your independent. Your independent variable is Q squared, and you're still U as being your dependent variable. So U is going to be the y-axis. This one is going to be the x-axis, namely Q squared, and you're going to plot it. It's going to be a line too, because Q squared over 2C is supposed to be a line too. When you plot Q squared, then here U. Please make sure in all of the graphs, you have to have properly labeled graphs. You have to have the scale properly correct. You have to have the, everything is correct. And you're going to find the slope using Excel if you like. And you can actually add an Excel file if you don't want to do it by hand, and include that Excel file in your lab report. So if you want to, you could do that, and that's going to save you from any problems in there. And you're going to find the slope, which is 1 over 2 C naught now, the slope. You're going to find the C naught from here, which is just going to be the slope. I mean, 1 over 2 slope, 1 over twice the slope. This is going to be your C naught from here. Again, you're going to compare it with the theoretical value. Okay. So you have calculated one from question 3, and you have measured it again in here with this formula. You're going to compare both of them. So there are 3 ways now finding C naught, the capacitance. Next, we need to make a graph of how U, this is the energy density, remember, depends on E squared. That too should be proportional to E squared, okay? So that too should be a line. Again, if you go back to the table, on one side you have the electric field squared, and on the other side you have the energy density. The energy density is your dependent variable, and the E squared now is your independent variable, and it should be a line. This is the formula that we're trying to find now. So now the constant of proportionality should be epsilon naught. The known value is 8.85 times 10 to the negative 12. Did you find that answer? So when you compare the two again, you're going to get an error. In your error, basically calculations, please be specific. Do not just say it's 2% or 1%. You have to refer to your data. You have to explain what you did and plug in the value there. Okay? I need you to be on top of this. You are really in control of this. If you have any doubts, or you think that there is a question that is not clear, please let me know or talk to somebody else. This is not a test. This is not an exam for you to pass. This is not something to test what you have already known. This is actually to help you understand how these things work and how to work them out to learn, okay? That is the purpose of the lab, really, for all of the lab activities. So this is not a challenge. This is something that is supposed to be helping you understand the physics behind it, but you have to do it, okay? Good? Yes? Very good. So now we're going to go to the dielectric. Remember, in the dielectric, we didn't really do a lot of it with it in class. So we're supposed to take, again, in this section, we will click the tab entitled dielectric, set the area again between 195 to 205. So don't put 200, whatever in the area in there. The separation D about 7.5 millimeter to 8.5 millimeter between the two plates. So it's kind of wide a little bit to be able to squeeze this material between them. And the maximum battery voltage to 1.5 and a minimum dielectric constant to 1 with 0 offset to begin. So basically, this is the things, okay? So the dielectric offset, dielectric constant is 1. Dielectric charge in here, what is this one? Show all charges, okay, that's fine. Capacitance, so we're going to do that. and then calculate now the capacitance. Remember, C naught, this is the real value based on your step for this part, okay? So now the value of epsilon C naught has changed because the area is not the same. The separation is not the same. So the C naught that you're working with is your own C naught now, whatever you come up with. So you have a choice a little bit for the area, and you have a little bit of choice in here when it comes to separation. Calculate the new value for C naught, okay? That's all that you're asked to do at this point, okay? So let me stop sharing the screen and go to the other place first of all. Share. Where is the FET? Oh man, I lost it. Oh, here, no, that's not it. Share. Did I close the window? That's terrible if I did. I don't see it. Oh no, it's because the other thing stopped. Okay, let me close this again. Share. And oh man, did I close everything in there? Sorry about that if I did. I did. Terrible. Let me go back into the page again. Sorry about that. And hopefully you guys have it up and running by now and doing all of the things as I was talking. So what is again the lab? So let me go back into the page, click on it, put it out, and load it. And then, by the way, if you have problems loading, it's because probably you have a Java that is required, a Java applet or something like that. Sometimes it has issues with that. So now let me share with you the screen. And it's loading. Okay. So we're going to go to the dielectric now, to this component. And this is basically what we're supposed to have. The area now needs to be something like anywhere between 195. This is good enough. Okay. And the separation is like, what is the requirement for it? Separation is, what is it? Between 7.5 and 8.5. So I have it too small, so I need to increase separation. 7.9, 8.1 is fine, or 7.9 is fine. So this is my numbers. Yours will be different, okay? So yours, first of all, if you just copy these numbers in your calculation, but you come back to it and you don't match them, you're going to have issues, okay? So don't do that, okay? So it says, so the dielectric constant, we're going to start with 1, okay? Let's show the capacitance now and how much it is, okay? And the voltage put at max in here. They said to put it at maximum. And the offset needs to be at 0. They want it to be exactly at 0? Yeah, it is at 0. Now it's fully inside, okay? So the dielectric is inside. And if I remove it, look at the capacitance now, it stays the same. So it doesn't really change. So it's you who is going to change that, okay? We're going to do that. By the way, I made a big mistake the other day in lecture. Nobody corrected me. When I put a dielectric in here, it's going to induce charges opposite to what you have in there. And that's how the separation drops in there, okay? So please, sometimes I'm not focused and things go completely south. So again, let me, we find epsilon naught. Based on my numbers, epsilon naught is equal to, epsilon, C naught is equal to epsilon naught times this area squared divided by this distance. But don't forget, I have a millimeter squared in here and a millimeter if I want to get it in farad. So I can find the number and compare it to this number if I want. So we have that. And let me go back into the instructions now. Stop and share. No, not that one. What happened to the PDF file now? It was like every time I do something else. Here is the LAB02 share. Okay, good. So now we have C naught. That's this question. Again, based on my numbers, this is the numbers I chose for D, and this is the number I chose for the area, properly converted to meter squared. This is the, and C naught is, and epsilon naught is equal to 2. So my C naught is, my capacitance for this case is C naught equal to, plug in the number, okay? You can use the picofarad if you like, or 10 to the negative 13, or 10 to the negative whatever. But as long as you're specific and clear about the units and everything else for this question. Again, now insert the dielectric into the capacitor and determine the value of the capacitance C in F. Enter, what is this one? C in farads, I'm sorry. Thought that there is another. Enter this value in the table below, change the value of the dielectric constant kappa, complete the table. So we're going to change kappa from 1, 1.5 all the way to 5, okay? And we're going to basically find the value of C now. Okay, so let me go back in here, stop sharing the screen, and share with you the FET simulation. So now we have the value H is 1, so we're going to go to 1.5. The value now has changed. This is not 1.5, 1.2 actually. I need to have 1.5 roughly. So if I can't get it, that's fine. It's exactly 1.5. How is that? This is the value of the capacitance. Now, when it was 1, it was the air, by the way. So the fact that I had this material in and out doesn't mean anything. It's still as a field of air, full of air, because this is where you control the capacitance, okay? I mean the dielectric. This is where you're controlling the material right now. So you're changing the material now. So you have 1.5. If you don't get it exactly, that's fine, okay? And then the next one is what? Let me look at the table. So it's going to be increments of 0.5, basically. Then 2. Okay, that's roughly 2. This is the value of the capacitance. So this is 2.5. Note the units have changed, okay? Oh, what is it? 2.5. This is good enough. So this is exactly 2.5. Then all the way to 5, basically. 5, it's still listing the correct values in here, so you can zoom out if you like to zoom out, okay? Oh man, now I don't like this. It does not give me, do I have to reset this thing? Reset? Yes. Okay. So if I reset all, you have to be careful, okay? When you do that for this specific part, it's gonna mess up your numbers, okay? Okay, so this whole thing changed now based on the new value, okay? So it's no good now. So you have to be very careful with these things, okay? The offset is 0. So this is the capacitance. If you reset, you have to recover back your old data for the plate area and also the separation between them. Are you guys know what's going on in here, don't you? I hope so. So what is the other part in here? Do you have any questions about this part? Very good. So basically, this is kappa. This is a relative permittivity. You start from material 1 all the way to 5. And in doing so, the capacitance now changes. Obviously, we need to make a graph. Now, since the independent variable is kappa, the dependent variable now is C. And when you draw, it's going to be a straight out line, because this is basically what you're drawing. What is the formula for it? I forgot. See, all the way to the top, probably. Here, you're drawing this line. C equals to C naught that you calculated already times kappa. So again, the slope is going to be your C naught. I mean, yeah, C naught. So the slope is going to be your C naught, and you're going to at some point compare it to the calculated value from this one. Again, these are your numbers now for C naught. This is not something preset. I'm going to go by what you tell me your numbers are in here. So if you don't tell me what your number in here for D and A, I wouldn't be able to tell, and you wouldn't be able to remember how did you find that value of C naught, okay? Which could lead to problems, in here in the graph and the data. So you really need to report those numbers. And you're going to lose points for that if you don't give me those numbers in here. And how you find this value of C naught. Once you have this C naught, you're going to, again, draw this graph, come back to this question, and basically find the value of C naught. And again, from the results of 11 and C naught, compare the two, and do they agree or there is a discrepancy between them. Part C for this lab. Part C for this lab, you're going to take 3 capacitors now and put them in series. And you have the voltmeter now to tell you how much voltage across them. And so basically, you're going to take 3 capacitors. One of them is 0.1 picofarad, 0.2 picofarad, and 0.25 picofarad. It may not be picofarads, okay? I think there is an issue with this one. But don't forget, okay, you're going to have the plate charge. You're going to have the total capacitance, the stored energy. You're going to need a voltmeter, and you're going to have 3 in series. So let me stop sharing this screen and go back into the lab, to the simulation. So we're going to come in here to FET simulation. So we're going to come into multiple capacitors now. And we need 3 in series, I'm sorry. 3 in series. And we need the total charge. We need the total stored charge. And this is the capacitance, actually. And the stored energy. We don't need storage. We need the voltmeter, actually. Okay. We need this guy to be set at 1.5. And now we're going to come in here with the red one next to the positive and the negative one. So right now, as you can see, the voltmeter is telling you the voltage is infinite because it's open. But when you close it, this is how you know that you have a good reading now, because it's not 0. This is 0.5, and the capacitance you're supposed to have. So the numbers that I told you about earlier are not correct. Okay, so they're all of the power of 10 to the negative 12. So this one maximum is going to be 3 times 10. So we're going to have, I don't remember the exact numbers in here for the capacitance. So you need to correct this one in here. It's incorrect. So it's not 0.1 micro. Oh, no, they're correct. 0.1 micro picofarad, 0.2 picofarad, and 0.25 picofarad. So the numbers are exactly correct. They are supposed to be the way they are. So let me go back into the. So this is 0.1 picofarad, actually, which is sent to the negative 13 farads. We need 0.2. So we need to move this one to 0.2. So this is 0.2 picofarad, slightly more, actually. I need to bring it down. Okay. And I need 2.5. This is way more than 2.5. Or it says 0.25 picofarad. So I have all of my capacitances now. This is the first voltage. I need the second voltage, so I'm going to bring it in here. And I need to bring this one in here. That's the second voltage. And this will be the third voltage in here. And if I want to find the overall voltage, it should be 1.5 volt, okay, from the top to bottom. It should be the voltage of the battery, which is exactly how much it is. So I can use my device to measure, for example, how much voltage between these 2 capacitors or between just one of them. And if I add this one, which is 1.8184, so that's just going to be the difference between 1.5 minus that one, which is going to be 3 point something. So between here and here is going to be just 3 point something. Okay, so it's exactly how the theory works. So again, let's go back into the lab instructions. Let me stop sharing that screen. Share the screen. So now we have all the setup correctly. And we want to record the values of the battery. The value of the battery is 1.5 volt. Similarly, find V1 across the first one. It was 0.78 or something like that. V2, how much it was, and V3, how much it was. And now what is the relationship with the voltages? You need to check that V, which is this voltage across the battery, must be the sum of this one plus this one plus this one. So you need to check this, okay? That they're actually, if you add up all of these three, it should be the same thing as this one. Using the given values of the capacitance, find the charges. Q1 should be, you have V1 and you have the capacitance. Remember, C times this one times V1, it should be Q1. The other V2, which is the second voltage that you measured, and you have the capacitance C2 that you have chosen, 0.2 picofarad. 0.2 picofarad times this value should be Q2. And the same thing, V3, which is that value that you calculated, should be this one. You need to check that these three, they need to be the same. Q1 and Q2 and Q3, they will be the same charge because they are in series, okay? Now, what is the total capacitance in farad? Read the meter, use the formula to find it. So you have two ways now to finding that, okay? So let me go back into share that screen. Where is the FET simulation? So this is the total capacitance. If I take 1 over 1 plus 1 over 2 plus 1 over 2.5 and invert the number, it should be the same as this one because they are in series, okay? And it should be less than the smallest of them all. The smallest is 1 times 10 to the negative 13. And this number is clearly less than that, okay? It's half, almost half than that. So I use the formula to find that. And I also compare it to this number. So I need to do both of them and see, do they match? Okay, so what is the total capacity? That's what's question 15. Now we're going to do the same thing, except we're going to be doing the parallel plates. Okay, so let me parallel capacitors. So let me go back into the FET simulation. And now it's the same stuff, except now we're going to choose 3 in parallel. Okay, and whatever values they tell me. So they tell me do 1. This one is probably 2. And this one is probably 2.5, maybe. I don't know. So we'll see. 2.5, maybe. Okay, good. Almost good. Okay. So now, if and the voltage stays the same, and this is how much capacitance, which should be just the sum of these 3. 1 plus 2 plus 2.5. That should be 5.5. Okay. Because they are in parallel now, and we need to compare it to this number, which is exactly how much it is right now. Okay, so let's go into the question in here first. Stop sharing the screen and share the lab activity. So again, Vmax should be 1.5 volt. And V1 and V2 and V3, they all should be for 1.5 volt. Okay, let me stop sharing the screen in here. And let's see if indeed it is the case. So this voltage across this capacitor should be exactly 1.5 volt. And it is, because they are in parallel now. This capacitor should be identically 1.5 volt also. And it is. This capacitor also should be under 1.5 volt. And it is. Okay? So everything is supposed to have the same voltage. The charges, though, they will not be the same. So let me go back in here. Stop sharing. Share. LAB02. So how are they related? They are identical because, again, this is a parallel configuration. Okay? So it's the same voltage across the battery. Using the given values of the capacitances, find the charge. Okay. Sorry, the capacitance now are slightly different. No, they are the same numbers. Okay, as before. So it's good. So now we have the voltage, which is 1.5, and we have the capacitance, which is 1 times 10 to the negative 13. So now you have C times V again. Plug in the number in here, plug in the number in here, plug in the number in here, and you should find different charges. They have the same voltages, but different capacitances, so the Qs are not like before, what I expected them to be the same, because this is a series configuration. Now this is a parallel configuration. It's a different story altogether. The voltages are the same, but the capacitances are not the same. Here, the charges are the same, but the voltages are not. As a matter of fact, if you check this, the voltages, they are different, and they add up to 1.5, okay? And now question, what is the total capacitance in farad? Read the meter. Again, the total capacitance was 5.5, 10 to the negative 13. And if you do the calculation, it should match. And the conclusion. Any questions about the lab?
Nope, pretty straightforward.
Okay, very good. I see you guys on, I'm gonna stop the recording right now. If you choose to stay in here, I'm going to also mute and turn off the camera. If you have any questions, please let me know. If you choose to do it later on, that's fine. You can leave, and I will see you if you do that on Monday. Okay? Let me stop the recording first.